Yeah, good afternoon, good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So today is our third session, which we will cover some of the practice problems related to the week three topics. So let's have a brief recap of what are the major things that are covered in the week three of this course. So the major portion was the transient conduction. So transient conduction, as you know, is a multidimensional conduction problem where the space and time coordinates are involved. So in week three or week two, we are discussing about the single dimensional conduction where the heat transfer or the temperature profile is a function of x only or y only or z only or any single dimension. But now we are going to the multi-dimension. So multi-dimension in the sense you can have the temperature as a function of x, y, z, and t. Or here we are mainly focusing on the transient conduction part where the temperature is a function of uh, space and also a time. Okay. First, that is the main essence of transient conduction part. Then, in the simplified transient conduction part is a lumped capacitance model, where uh, where we assume that the temperature inside the body is isothermal. Okay, so that is the lambda capacitance model. So that's not a multidimensional problem. So it's like it's a the temperature is a function of only the time. Okay. So then that's a simple case of transient conduction. But when we go to the when the so in that case we studied how we can use a lumped, how a system can be assumed as a lumped system. So when the Biot number is less than 0.01. So if that is not the case, we cannot assume it as the temperature field inside the body as isothermal. So we have to consider the temperature variation, the spatial temperature variation of the body when the when for a higher Biot number cases. So in that case, it's like a temperature profile in a semi-implicit case, or we can have other means like supply by using we can solve the one-dimensional transient heat conduction equation with the with the norm separation of variable method and all that were also discussed in the and the solutions and all were also discussed in the class. So here we will solve some of the problems related to that topic. So let's get started with the first problem. Sorry. So this is a here we have a the heat transfer coefficient of air flowing through a sphere is to be determined by observing the temperature time history of the sphere, which is fabricated from a pure copper. Okay, and the dimension of the sphere is given, which is 12.7 mm, and initially which is at a 66 degrees Celsius temperature, and it is inserted into a air stream which is at 27 degrees Celsius temperature. The thermocouple on the outer surface of the sphere indicates 55 degree after 69 seconds, which is inserted into the air. So we have to assume the sphere behaves as space-wise isothermal. Space-wise isothermal means the temperature gradient within the body we can neglect, which means we can consider this case as a lumped case, and and we can solve the question. So you may please try. Then after that, I will solve it. Solve it. Initially, so the initial condition, the we have a sphere whose diameter is 12.7 mm, which is at a temperature of 66 degrees Celsius. Then this sphere is inserted into an airstream, which is at a temperature of say 27 degrees Celsius, and it has a heat transfer coefficient which we need to find out, that is h. And after it is given that after 69 seconds, the temperature of the ball sphere reduces to how much? 55 degrees Celsius. So these are the given information. So anybody got the answer? Okay, as it's already mentioned that in the sphere is a space-wise isothermal, we can assume this as a lumped, assuming assume lumped system. Assume it as a lumped system where the so what is the rho v c, that is the rate of change of temperature of the board, should be equal to the energy that is convected out to the airstream. So if you solve this equation, so I am not solving this, is already solved in the lectures. So if you solve this equation, you will get t minus t infinity, that is t at any time instant. Okay, a temperature at any time instant minus t infinity divided by the initial temperature Ti minus T infinity should be equal to e raised to minus HA by rho CPV times the time. Okay, so this is just the temperature profile we will get if you solve this equation. So this solution is very simple. So it's okay. We can also try by your own. So now we have every point, every data, right? We are given Ti, which is 66 degrees Celsius. T infinity is not 27 degrees Celsius. Then H is given how much? H is the one we need to find out. Rho, Cp, K, everything is given in the question. And also time is also given. That is T at T is equal to 69 seconds is given as 55 degrees Celsius. So the everything we required is given. So only we need to find out is like V by A, which is, or A by V, which is equal to R by 3, which is equal to D by 6 for a sphere. Okay. So how to calculate this? So V by A is equal to volume of the sphere is 4 by 3 pi R cube divided by the surface area of the sphere is 4 pi R square, which will give R by 3. Okay. So this is 55 minus 27 divided by 66 minus 27 is equal to e raised to minus h is what we need to find out. T is given 69 divided by 8933 into 386, that is Cp, into V by A. I am replacing it as D by 6. So that is T is 12.7 mm. Okay. So if you solve this equation, you will get H as 35.7 watt per meter square Kelvin or degree Celsius. So, any doubt in this question? This is a very simple question. It's direct application of the lambda analysis. So, uh,
Sir, what will be how to proceed when Ti is equal to T infinity?
T I is equal to T infinity, then there won't be any heat transfer, right? If the initial temperature and the airstream temperature are same, there won't be any heat transfer.
Okay.
Okay. So we will move on to the next question. Here we have a aluminum slab having a volume to surface area ratio of 0.025, which is at the initial temperature of 25 degrees Celsius. So the aluminum slab is heated with a hot air stream with the gas temperature and the convection assumed to have constant values of 600 degrees Celsius and 100 watts per meter square. Okay. So how much, how long will it take to achieve 75% of the maximum possible energy storage? So here also a similar question like previous one. Here we have a aluminum slab whose V by A, that is the volume to surface area ratio is already given, which is basically you are given directly the characteristic like LC, uh, and which is initial temperature is 25 degrees Celsius. So it is heated by a hot gas stream, which is at a temperature 600 degree and a convection coefficient of 100 watt per meter square Kelvin. So we want to find out how long will it take to achieve 75% of the maximum possible energy storage. Okay, first before proceeding, we have to check whether we can use lambda analysis here or not, because here it is not given that we can take the temperature as isothermal, or in the question it is not mentioned that we can use the lambda capacitance model or the lambda analysis directly. So first we have to find out what is the Biot number, which is LH times characteristic line divided by the thermal conductivity of the solid or the slab. So H is here, it is given as 100 into length LC, that is a characteristic length. It is already directly given 0.25 divided by the Ks, that is 231. So if you do this, you will get as 0.0108. Okay, which is less than 0.1. So we can lumped assumption is valid here. Okay. So now we can confidently use the lumped assumption in this question. So We know the temperature profile. I already discussed in the previous question. The temperature profile for analysis is T. Okay. This parameter, that is HA divided by rho CPV, or the inverse of this, the inverse of rho CPV by HA is known as the time constant tau. Okay. So I'm replacing this rho CPT by HA as tau, which is the time constant. So I'm rewriting the temperature profile T by tau, or I'm writing this as theta by theta I, or theta is equal to T minus T infinity. I'm just simplifying this. So the temperature profile theta is equal to theta I e raised to minus T by tau. Okay. So now we have to find out the heat transfer to this lab. Then only we can find out the maximum possible energy storage. Means how much heat transfer it can, that is, means energy storage means how much heat it can store. Okay, so for before that, so before maximum possible heat transfer, we need to find out what is the expression for the heat transfer to the amount of heat that is transferred to the block. That is, we know q q at any time is equal to h a theta, right? Or we can say h a theta I e raised to minus T by tau. This is the heat that is entering into the block at any time t, any time instant t. So if we want to get the heat transfer over a time period, what we need to do? We have to integrate, right? So t for a time period. So the total heat transfer from 0 to a particular time t, that is integral 0 to t ut dt, which is equal to integral 0 to t h a theta I e raised to minus T by tau. Okay, so if you integrate this, theta I is a constant, e raised to minus T by tau divided by minus 1 by tau from t to 0. So the total heat transfer from 0 to t is equal to h a theta I times tau 1 minus e raised to minus T by tau. Okay, this is the one. If you will get if you put the limits. What is rho CPV by HA? So the rho CPV theta I 1 minus e raised to minus T by tau. So this is the expression for the amount of energy that is stored by the uh, block or the aluminum slab from 0 to a particular time instant t, or from 0 to t. Okay, so when this so we are when this quantity will become maximum, this will become maximum when this part becomes 0, right? Or at t is equal, t tends to infinity, the maximum amount of heat gets stored to the slab. So, okay. So when this part becomes zero or at it so it won't so, so for say for example if you see the temperature of the aluminum slab will exponentially reaches to this gas stream. It won't be the exact value of 66 degrees Celsius. Okay, sorry, not 66, 600. It will exponentially reach if you see the curve. So at t times tends to infinity, we can say that it has a maximum possible heat transfer happen. So or the so Q max. So the maximum amount of energy it can store is when at t is equal to infinity. So which is rho CPV theta I. So in this question, we need to find out the time at which how long will it take to achieve 75% of the maximum possible heat transfer. So if we equate this Q at any time should be equal to points sorry Q from 0 to that time or a particular time where it reaches 75% should be equal to Q max. So if you substitute, you can cancel this. So if you so for that you need to calculate what is tau, that is time constant, which is rho CPV by HA. So this will be 2702 into CP 1033 into 0.025 divided by H. It is 1500. It is if you substitute in this value, you will get the T as 967.34 seconds. Okay, so it will take the slab will take around 967.34 seconds to reach the 75% of the maximum possible energy storage. So any doubt in this question?
No, sir.
Okay. So then we will move on to the next question. A stainless steel.
Sir, can you show me the second page? Because, okay, sir.
I think you these slides are shared. No? You are getting the slides. So
I don't know, sir.
because you are registered for this course now in the course page at last means there is a problem solving session like link is there. Okay, so if you click that you will get an excel sheet. So in that
Where?
excel,
Sir, where?
so if you go to the course page, right, of this course, that is heat transfer, in the left side you will get a tab, right, week 1, week 2, week 3,
Okay.
right. Okay, at that at bottom you will have a problem solving session. One link
Okay.
will be there. So if
Okay.
you open that link, it will go to a Excel page.
Okay.
So in that Excel page, you will get the folder link to this course, means where I upload all these uh, presentations.
Okay. Thank you.
So now we can solve this question. So a stainless steel spherical shell satellite of 3-meter outer diameter and 1.25 centimeter wall thickness re-enters the atmosphere from outside space. If its original temperature is 88 degrees Celsius, the effective average temperature is and the effective average heat transfer coefficient is 117 watts per meter square Kelvin. Estimate the temperature of the shell after re-entry, assuming the time of re-entry is 10 mm, sorry, 10 a minute, and the interior of the shell is evacuated. We can try in the similar manner. So say it's a similar question. The effective average temperature of atmosphere. Okay. I got the answer. So first we need to check whether we can use lambda analysis or not. So we will find the Biot number HLC divided by KS. That is LC, which is V by A. Because it is a very spherical shell or a very say shell, we can write the volume as the thickness. That is, I am writing the thickness of the shell as. So if this is okay, so this is the shell. So I am mentioning this thickness as dr. Okay, so the volume of this shell as 4 pi r cube, or sorry, r square times dr, as it is a spherical shell divided by the surface area 4 pi r square. So the characteristic length is dr. Okay, or the thickness. So if I put it here, you will get h. Yeah, h is 115 into thickness is given 1.25 centimeters. K is given 14.4. So we'll get it as 0.098, which is less than zero point 0.1. Hence we can we can use lumped analysis is valid here. Okay. So we'll use our temperature profile for lambda analysis. So the given values are T infinity is the temperature of atmosphere 1093 degrees Celsius, and the temperature at which initial temperature is 38 degrees Celsius. We are asked to find out the temperature after 10 minutes of re-entry, which is after 600 seconds. So temperature at T minus T infinity is 1093 divided by T 38 minus 1093 e raised to minus H is 115 time 600. So V by A, that is, I'm bringing it the denominator, which is the characteristic length. So rho is given 77817 into 461 into, so if you solve this, you will get the temperature of the body or the spherical shell at T is equal to 600 seconds as 864 degrees Celsius. Okay. Any doubt in this question? I think it's a similar kind of question. So, okay. Then we will move on to the next question. So, this question is a little bit different question. So, the copper wire of 0.8 mm outer diameter and 5 centimeter long is placed in an airstream whose temperature rises as it's a function of T. Okay. The earlier questions was what we done is the the ambient air is a constant. Now it's not a constant; it's a function of time t. Okay. The initial temperature of the wire is 10 degrees Celsius. We have to determine the temperature of the wire after 1 minute. So the heat transfer coefficient of air and wire is given, and the properties of the copper wire are also given. Okay. So the difference is here temperature T infinity is not a constant. It's a function of time. So we have to consider that also. First, we should check whether we can use the lambda analysis or not. That is, bad number is HLC by KS. So LC is V by A. V is pi R square in times the L, that is the volume of the cylinder, divided by the surface area, that is pi RL. Sorry, 2 pi RL. Pi cancel. So it becomes R by 2, or we can say D by 4. So H is given how much? 40. LC, that is D by 4, 0.8 into 10 raised to minus 3, K 391. So if you check, this will be Can you please calculate and say what is this value?
Sir, 8.2 into 10 to power minus 5.
How much?
8.2 into 10 to power minus 5.
Yeah. Okay. So it's already in the order of -5. So which is less than anyway less than 0.1, right? So we can use the lambda assumption. Is valid in this case. So, so now you can use the lambda assumption. So what is the general equation for lambda analysis? That is rho v cp, or we can write c times dt, so the change in temperature should be minus ha t minus t infinity. Okay. So this is our static equation. So in the earlier case, this t infinity was not a function of time, or t infinity was constant. But here T infinity and T, both T, the temperature of the wire, and also the ambient temperature is a function of time. So this leads to another governing equation, like I am writing T by dt plus minus HA divided by rho Tc. For the time being, I am writing this as a, for M for the calculation purposes. So T minus T infinity, the function is given. Okay, that is 10 plus 40t. Okay, so if you rewrite the governing equations, minus m t minus 10 minus 14t. This is our governing equation for this problem. Okay, we have to solve this governing equation to find out the temperature. So how to solve this? So if you rearrange this, okay, you will get like this. So this you may be familiar, this kind of differential equation. This is of the form dy by dx plus py is equal to qx. Here y is the temperature, x is the means x is the t. That's only difference, and p is a constant. Here q, which is which we can write, that is mt, or which is a constant, and it's like a some some constant into the function of x. Okay, so this equation is in this form. So this the solution we already know, that is e raised to integral. So we have to have an integrating factor, that is e raised to integral a dx, like here p is m and dx is t. So we'll get e raised to integral mt. So the equation is, so the solution is t into integrating factor is equal to integral this m times 10 plus 40t into integrating factor times plus c. So this is the solution. Okay. So you have to solve this equation. So if you solve this equation, you will get the final T as so this will be the solution of this equation. So for finding out C, that is one integration constant, we know one boundary condition like at t is equal to 0. So at t is equal to 0, the initial, what was the initial temperature? 10 degrees Celsius. T is 10 degrees Celsius. Okay. So 10 is equal to 10 plus 14 into 0 minus 14 by m plus c times e raised to 0, 1. So c will be 14 by m, which is for that we need to find out what is m, right? So if you find out m, which is how much, ha divided by rho vc, h is given, that's 40 rho 9190 c 383, and the v by a you already d by 4, that is d is how much, 0.08. So this will approximately around, it will, if you calculate, will come out to be around this much, and the c uh, will come out 40 divided by, yeah, it will come out to be around 246. Okay, so now you know every factors like m, you know, c, you know, so the general equation will be 10 plus 14t minus 14 by m plus 246 raised to minus mt. So you can substitute the value of m also the final equation and rewrite to some reduced form also. Okay. So now what is your question? So we got the temperature profile. We need to find out the temperature after 1 minute. Okay. So if you put t is equal to 60 seconds into this equation, you know everything. M is already find out. So if you do the calculation, you will get temperature at 60 seconds as around 612.42 degrees Celsius. Okay. So I hope you understand this, because the only difference is the now the T infinity, this one is a function of, which was constant earlier, is a function of temperature, sorry, time now. That's the only difference here. So we need to do some extra. So the differential equation, so the governing equation of changed, so the differential equation also changed. So we have to solve that differential equation. So that's the only task in this question. So I hope you understood this. Okay, then I will move on to the next problem. Here we have a thermocouple junction, which is approximate as a sphere, is to be used for temperature measurement of the gas stream. The convection between the junction and the gas is 400 watts per meter Kelvin. Along with convection, we have the radiation heat exchange also. It encloses the gas. If the duct wall is at 400 degrees Celsius and the emissivity of the thermocouple bead is 0.9, calculate the steady state temperature of the junction. That is the first question. First, as usual, what we should do, we should check whether the lambda analysis is valid or not. Can you please check and say what is the Biot number for this case? So it's like it can be approximated as sphere. So the LC, that is the characteristic length, is how much? R by 3. So we can calculate from that.
Dia of the sphere is not given. Hello.
Yeah, 1 minute. Okay, dia is not given. Okay, let me
Yeah.
check the question. We can take the diameter as around 7 mm. Okay, sorry, 0.7 mm. But actually, for this question, means just to find out the steady state temperature. So there is no need of checking for lambda analysis, but just check whether the this can be treated as lambda analysis. So diameter we can take as 0.7 mm. So Biot number is h by k, that is t by 6, right? 400 into k is 20.
So 2.3 to 10 to the power minus 3.
How much? 2.3.
10 to the power
Anyway,
minus.
this is less than 0.1, so we can have the lambda assumption. But anyway, for this question, actually, whether this is needed, no, because you are asked to find out the steady state temperature of the junction, right? So at steady state, what is meant by steady state? So the temperature is constant, okay. But this helps us to assume that the bead is The inside the there is inside the bead there is no temperature, non uniform, or the temperature profile is isothermal. So at steady state, what happens at steady state?
No change in rate of heat transfer.
Yeah, the temperature will not change, right? So if you see in this question, we have the sphere. So we have the temperature thermocouple junction, which we can assume it as a sphere. It is it is it is we have kept it in a stream of gas, flowing gas, which is at a temperature of how much? That the temperature of the gas is also not given. Let me check. Yeah, temperature of the gas you can assume it as 200 degrees Celsius. So the convection is used to measure the gas. The gas temperature is some part has missed when I copied the question. So the gas temperature is two. You can take gas temperature as 200 degrees Celsius. So we want to measure the temperature of this gas stream using this thermocouple junction. Okay. So but there is the so we have the radiation exchange. So the gas of the ducts of the wall of the ducts where this gas is moving is at a higher temperature, which is at 400 degrees Celsius. Okay, that is what the question is given. So we have a radiation exchange. We have in this case we have to consider the radiation exchange also because the temperature is very high and also the emissivity of the bead is given. So indirectly, what we are saying is we have to consider the emissivity. So how the steady state attains? The steady state attains when the net radiation exchange between the junction or junction in the means the thermocouple and, and the wall, which is at a higher temperature, that is 400, is balanced by the convection loss from the bead to the gas. Am I right? Initially, the temperature means initially the heat both from radiation from the wall and the gas stream. From the gas stream, it will be the thermocouple temperature will increase, but after 200 degrees Celsius, okay, the now the heat transfer happens from bead to the gas. So when the radiation heat, whatever the heat that the thermocouple bead is getting by radiation, that should be convected. That should be convected to the flowing gas, right? Then only the steady state attains. Do you agree?
But sir, we will agree to it when the only radiation from the wall is used for heating. But here the case is different. That
No, what I am saying is up to 200. After 200, the temperature of the after two up to 200, the both from both heat transfer is there, right? From radiation, the thermocouple junction is receiving energy, and from the convection also it is receiving energy. But the point where the temperature reaches above 200 degrees Celsius, from the bead, the heat transfer takes place to the gas by convection. But
yes,
still the ra- but the
sir.
still the radiation is happening.
Okay, that is true. And
Yeah,
then you were saying that the BO number we have to check. There is no need of checking BO number because steady state has achieved.
ah, yeah.
So, but when the steady state is there, still the temperature profiles may be there.
I'm
That
saying the temperature profile within the bead. If
yeah,
the
within
temperature profile within the bead, we are taking isothermal. That's why we are checking Biot number.
So, so it is it is necessary to check now,
Yeah, it's
or is it
yeah.
optional?
No, it's actually in this case means as it's a steady state condition, and in this case mean like this is for very small objects. You see, it's like zero point 0.7. So you can check. It's better to check the
Okay,
Biot number.
okay, 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 sir.
So we just need to equate the radiation heat exchange and the convection heat exchange. So what is convection heat exchange? The heat transfer coefficient times the surface area of the sphere, temperature of the sphere minus T infinity, that is the temperature of the gas stream, should be equal to the radiation heat transfer, that is emissivity sigma, the surface area T of wall raised to 4 minus T raised to 4. Okay, this got cancelled. So H is how much? Uh,
400.
400 into T minus 200 is equal to 4 and 9, 5.67. T wall is 400 raised to 4 minus T. So you have to solve this equation to get T. Okay, so if you solve this equation, you will get degree Celsius. Either you can use MATLAB or something to solve, or you should try some trial and error method. Okay, because uh, yeah, here you just fourth power. So if so you will get the steady state temperature of the bed as 218.7 degrees Celsius. So we will go. This is also a continuation of the question, the previous question. So we have to determine the time for the junction temperature to increase from an initial condition of 25 degrees Celsius to temperature that is within 1 degree of the steady state. So initially the temperature junction temperature was 25, and we have to find out the time it taken to increase from 25 to the or within 1 degree Celsius of the steady state, which means how much? You can take the T as 217.7. So the time required to increase from that to that, we have to check. We have to find out. How we will find? Oh, this I will write the governing equation, that is E10 minus E out is equal to E. Okay. So initially there is no E out, only E in. So what are the heat transfer that is coming in?
That is due to convection by the gas plus
Yeah, HA T minus T infinity minus T, right? That
plus
is,
radiation mode will also be there.
yeah, plus sigma A T wall raised to 4 minus T is equal to rho this is the equation. So this equation you cannot solve it uh, directly. You need some like numerical techniques to solve this. So I just want to show how we need to accommodate the radiation part also. That was my intention. So if you solve this equation, so if you are interested, you can try solving this out. So if you solve this equation, you will get the time, means time as around 4.9 seconds. So just to cross verify, you can check that is t is equal to 4.9 seconds. Like from to increase from t is equal to 25 to 216.7. Sorry, 217.7 degrees Celsius. So let's move on to the next question. So here we have a large slab of concrete of thickness equal to 200 mm is exposed to high temperature radiant environment on one side. So we have a slab. We have a slab of thickness 200 mm. The surface facing it, I'm taking this as x. This is this is exposed to a temperature of 125 degrees Celsius, and the other side is there. This is a side where it is exposed to high temperature, and this is the other side. Okay, the slab was initially at temperature of 30 degrees Celsius, and the thermophysical properties is given. Okay, so we have to determine the time taken by. So actually, this there is some mistake in this uh, expression. So what we need to find it? We need to find out the time required for the temperature to reach this condition. That is T of slab at any time minus Ts divided by Ti divided by Ts minus Ti as point as 1%, which is 0.01. So that which means we have to determine the time taken by the lower temperature profile for the difference, the quantity where the difference of lower temperature profile with the initial temperature to the uh, higher temperature side, the difference of high temperature side with the initial temperature as 1%, like 0.01. So this is the condition we have. That is the other side. So T of x is equal to L T. Okay. And we are asked to find out the concrete slab as a semi-infinite solid. So in semi-infinite solids, like we cannot assume the lumped analysis. Okay. So in the lecture, it was already taken the heat transfer, which the professor has already discussed the heat transfer through a semi-infinite solid. I hope you were able to recollect that. So we have to use that principles to solve this equation. We cannot directly solve using the lumped analysis. Okay, we have to use the solution of semi-infinite solid. So first we will calculate what is the uh, can you please calculate what is the thermal diffusivity? That is K is equal to rho by K by rho C. K is already given, that is of the slab as how much, 1.06 divided by rho 2150 into, and can you please calculate this answer?
5.2 to 10 to power minus 7.
5.2 into 10 to the minus 7 meters square per second. So I hope you remember the one similarity parameter which was introduced. That is, what basically what we get? It's a function of both x and t, right? So the one-dimensional heat conduction equation reduces to dou square t divided by dou x square is equal to 1 by alpha dou t by dou t. Okay, so this is the governing equation for this. But this is a partial differential equation. So what we need to do is we need to convert this partial differential equation to a ordinary differential equation by using a similarity variable known as eta, which is found out as x divided by 2 root alpha t. So what is the benefit of this similarity variable? The similarity variable will account for the changes in both x and t. So if you substitute this into this equation, you will get, I'm not going into the solution, it's already discussed in the class, you can refer back to the lectures. So you will get a one-dimensional, ordinary differential equation. And if you solve that ordinary differential equation, you will get the temperature distribution. That is how you need to proceed. Okay. So the eta, that is the similarity variable, is defined like x by 2 root alpha t. So, and the solution is t minus t of xt minus ti divided by ts minus ti is 1 minus error function of eta. Okay, this is the solution of this problem. So here we have to, the eta is given. So this is what we are given in the question. 0.01 is equal to 1 minus error function of eta. Okay, so or 1 minus error function means it's like a complementary error function. So you can use we have the error function charts. So you have to go to that chart, or it's you can directly Google the error function calculator, the inverse error function and error complementary error function calculator, and if you use that, you will get the eta as around 1.82. Okay, corresponding to this equation. So you get eta is equal to 1.82. So if you substitute this back in this equation, that is 1.82 is equal to x. What is our point of interest? X. What is x here? Where we need to this x, this t is where it is defined. It's where it is asked for the question, right? At the other end, right? At the other end of the slab, which is at x is equal to L. So L divided by 2 root alpha t. If you substitute this, you will get the equation for it. You will get t, because everything is known. L is equal to 0.2 meter. Alpha we already find out 5.2 into 10 raised to minus 7. So you will get t as, can you please calculate this and say what is t? You will get t as around 5817.2 seconds. You can verify later, or if you're getting the answer, you can cross check. Okay, so this was at if you have any doubt, you can refer back to the lecture of this infinite slab. How we got this equation, like how it was discussed already in the lecture. That's why I'm not re-repeating it again. Or you can refer to any standard heat transfer textbooks. This derivation is clearly mentioned. So this the next question is a continuation of the previous question. We have to find out how much heat would have transferred to the lab to the slab during this period per square meter. Okay. So for that we have already have the temperature profile, that is T minus, I'm not writing it's like T of x of t, x and t is equal to 1 minus error function of eta, where eta is equal to x divided by 2 root alpha t. Okay. So to find out the heat transfer, we need to find out what is the heat flux at x is equal to 0, because heat is getting transferred from that left side face, right? So the heat flux at x is equal to 0 is, for that, what is q is equal to minus k dt by dx at x is equal to 0. Okay. So what is eta? Because we are everything we are writing it in terms of eta. So we are replacing x with eta, that is d eta is equal to dx divided by 2 root alpha t. So if you write this, you will get minus k by 2 root alpha t dt by d eta at eta is equal to 0. Okay, okay, at any time instant. So if you differentiate this, so where this value, if you have to differentiate this value, that is we got t of x of t is equal to ti plus ts minus ti into 1 minus error function of eta. So we have to differentiate this value d by dt, sorry, d by d eta. Okay, it's basically a derivative of this error function. So if that also you can refer to internet, the derivative of error function. So if you differentiate this, you will get it as minus 2 divided by root pi ts minus ti. Okay, if you differentiate this, you will get this value. So the heat flux q of t, you substitute back, minus k divided by 2 root alpha t into minus 2 divided by root pi ts minus ti. 2 cancel. So the heat flux at any time at x is equal to 0, that is important, that is in the left face, is k Ts minus Ti root of pi alpha T. Okay. Now we have to find out the heat transfer during this entire period. That is Ts. That is at T is equal to, we already found out earlier how much? 5817.2 seconds. Up to this, from 0 to this much, how much heat has transferred to the slab? That is what we need to find out. So we have to integrate it dt. So if you integrate, so if you do the integration, you will get the final answer as 2k Ts minus Ti root of T by pi alpha. Okay, this is the total amount of heat that is transferred to the slab from T, from 0 to a time T. Okay, so then now we can substitute T is equal to 58.2. So please just substitute this and say what is the value. Can you please write this, calculate this?
Sir, it is around 59,888.
Hello, this is my answer. Means I have the answer I am getting. So uh, you can please cross check later, and if this is wrong, you can just intimate me in the next class. Okay, please check whether some calculation mistake. I will also calculate once more. Then. Yeah, still I am getting this answer. So can you please cross check?
Yes, sir, it is 12.24 into 10 to the power 6.
Okay, yeah, somewhat near.
Yeah, yeah.
That's fine. Okay, so let's move on to the next question. So this we have a one-dimensional plane wall with a thickness of 0.1 meter, initially at a uniform temperature of 250 degrees Celsius, is suddenly immersed on an oil bath at 30 degrees Celsius. Assuming the convection heat transfer coefficient for the wall and the bath is 500, calculate the surface temperature of the wall 9 minutes after immersion. So first thing what we need to do is what we need to check the biot number. So we have a plain wall, so I'm making as 12. So both sides immersed in a water bath, which is at the infinity of 30 degrees Celsius. So please calculate the biot number.
What will be the critical length here? Because it is, I think, semi-finite case.
Mhm. Almost.
Critical length.
Just 1 minute. Yeah, sorry for the. Yeah, what was you telling?
Pardon, sir?
Yeah, the length thickness you can means the LC you can take as 0.1.
It's coming out to be 1.
One. Yeah.
Yeah.
So we cannot use the which is greater than 0.1. So we cannot. The lambda analysis is not valid here. The lambda analysis is not valid. Okay, and this is not a semi-infinite case also. We have to use some uh, like charts. So if you are provided with charts, we can use this. So this is a case. This is I'm just showing the example, just how to use the chart. Okay. So the procedure was so that you can apply to other procedure also. So this is a chart that I have taken from a textbook known as Incorpora. So this is the midplane temperature chart as a function of time for a plane wall of thickness 2L. Okay, use with permission. Means this is from Incorpora, right? And this is another temperature distribution uh, in a plane wall of thickness 2L. Okay, these two charts we are using to find out the or the find out the answer in this question. So first, what we need to find out the surface temperature of the wall. So let's first look to the first chart. So here, from the first chart, we cannot find out the surface temperature because the first chart is theta O by theta I, which is it is giving the midpoint temperature. Okay, so this first chart will only give you the midpoint temperature. But using that midpoint temperature, we can find out the temperature at any location X. So by using the data from the first chart, we can find out the surface temperature. Means by putting that value in the second chart, it is this is chart one, this is chart two. So by getting some data in from this chart one and by substituting in this chart two, we can get the required surface temperature. Okay, so if it was midpoint temperature, if it is asked in the question, so only the first chart was required. As it is, as for the surface temperature, we have to use the second charts. So one problem is here. Now, when we are defining biot number or when we are using the charts, we should check how they have taken the uh, dimensioning and also how they have calculated the biot number properties. Here, the plane wall of they have taken the thickness of the plane wall as 2L. So that's why I also use the same nomenclature, that is 2L. But the the biot number they are taking is H. It is inverse of biot number, this one. So the biot number they are taking is HL by K. Okay. So so the biot number that we have calculated here is wrong. We have to take L, right? So L means 0.1 by 2, which will be 0.5. Am I right? So when we so we should be careful when using the chart. How they have taken, how they have defined the biot number, and all we should be. So the same way also we should also define. Okay, while using the chart.
But the point 1 by 2 here will be 0.05. So is that available 0.05?
Hmm?
Point 1 by 2 will be 0.05 now.
Yeah,
So is that value can be read for 0.05?
0.05. I didn't get it. Is that value?
Sir, actually that point 1 by 2 we have taken.
Ah,
So point 1 by 2 will be 0.05.
0.05. Yes,
0.05. So can we read that from 0.05 here?
0.05.
Yeah,
Which one?
point 1 by 2 will be 0.05. We are reading 0.5.
Okay, then some. Let me check. Uh, 5 500 into 0.05 is 25 divided by 50 is zero point 0.5 only. No?
Okay. Okay, sir.
Is this right? Yeah, I think this is right. Zero point 0.5 only. Yeah, yes, this is zero point 0.5.
I thought that you were taking L, not that you are taking pure number there, na?
Yeah, but the problem is initially I took 2L because, but the problem is when we are using charts. So when we are using chart, we should check how they have defined the biot number. Initially, I missed that part. Okay. So here you see, here this chart is defined for a plain wall of thickness 2L. So which means our thickness 2L is 0.1. 2L is 0.1. And they have defined biot number as HL by K. So their characteristic length is half of the plane. Okay. So that's why I redefined the biot number. So before, when we are using chart, first we should check how they have defined the quantities. Accordingly, we have to name that or reframe our question. Not just write our given parameters in the question. Okay. So the Biot number is we already find out that is zero point 0.5. So the inverse of Biot number, how much? So the Biot number inverse is 1 by zero point 0.5, which is 2. So the next parameter we need to find out is the Fourier number. Okay. Fourier number is alpha t by L square. So alpha is, so I'm not calculating the alpha because you can try alpha, that is alpha is equal to k divided by rho cp. So k is given, rho is given, cp is given. So this will come out to be around 1.37 into 10 raised to minus 5 into the time, how much? 9 minutes. So 9 into 60, the whole divided by L square. L square is 0.05 the whole square. So this will come out to be around 0.2.96. Okay. So now we got the parameters, uh, Fourier number and the Biot number inverse. So now we are plotting on the graph. So Fourier number is 2.9. So we can take approximately as near close to 3. So this is the vertical line. Okay. Now the Biot number inverse value is 2. So this is our 2 line. So this intersects somewhat here. So our required ratio, that is from the graph, the required ratio theta I by theta O by theta I is equal to, we got 0.3. Okay. So from that we can find out what is the midpoint temperature. It is theta O minus T infinity divided by theta I minus T infinity is 0.3. So theta O is equal to 0.3 into 250 minus 30 plus 30, which is equal to 96 degrees Celsius. Okay. So this is not what we need to find out. We need to find out the surface temperature. For that, we have to use this graph. What is Biot number inverse? We already found out it as 2, right? So this is our, so this is our 2 line. So surface temperature, surface means What is x by L at surface? What is the value of x by L at surface? It is 1, right? Because surface means at x is equal to L. Because I am defining S as the midplane. So we have to find out what is 1. X is equal to 1. So this is the x is equal to 1 line. So this intersects somewhat here. So this is our value. So theta by theta O is equal to 0.8. So we can write here. So t at x is equal to L minus t infinity divided by to minus t infinity is equal to 0.8. Therefore, ts is equal to 0.8 into 96 minus 30 plus 30 is equal to 82.8 degrees Celsius. Okay, this is how we have to use chart. This is how we use charts to find out the temperatures at different locations. I hope this was clear to you how to use chart. So the one question is there is this is also using chart. So this is for a cylinder. So I'm giving this as a homework to you. Okay, the same way you can use. So first, before defining this RO, biot number and all, check how they define the uh, 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 parameters and the biot number, Fourier number and all. So then the similar way you can proceed like first. So here only one chart is required. That's why I have given the required number of charts. So you can try this and come in the next class. Okay. Uh,
Okay, sir.
yeah. Thank you. And this comes to the end of our section. I hope uh, the session was useful to you and you learned something new. So thank you everyone for joining the session. So see you the next week. Have a nice week ahead. Thank you. Thank
Thank
you.
you. Thank you, sir.
Thank you.